Alrighty, hopefully you have a really good solid understanding of groups or families and periods now that you've had some practice with that. And we're going to go even deeper into the periodic table today. Now, I had you read the entire section in your book. I do not expect you to know all of the different words that they mentioned in there. I don't expect you to know, well, what are the alkali metals and what are the alkaline earths and what are the transitions and the inner transitions. I'm not overly concerned about that, but here's what I do want you to know from that section. Okay, first of all, there is a black stair-step line that goes part of the way down the table, and you should be able to see that on your periodic table as well. Anything to the left of that stair-step line, so all of this over here, as well as these elements down here, all of those are metals. Now, you're familiar with metals. Properties of metals include things like they're shiny. You can roll them out into a sheet. You can draw them out into a wire, so they're ductile. That's what that word means. You can draw it out into a wire. They are very good at conducting heat and conducting electricity. So everything over here is going to be a metal. Everything to the right of the stair-step line is a non-metal. And non-metals have the opposite properties of metals. So in place of being shiny, they're going to have just the opposite kind of texture. They're going to look much more dull in luster. They're going to be very brittle. If you try to roll them out or if you try to draw them into a wire, they would just break into pieces. They do not conduct electricity very well. They do not conduct heat very well. These elements that are along the stair-step line, now aluminum is an exception, and you'll notice that I don't have that one colored on your periodic table in your book. They are purple, and I've kind of used a purple color here as well to color in these 7 elements, and they are called metalloids. And a metalloid, because they're located in between the metals and the non-metals, means that they're going to have characteristics of both. They're not fully a non-metal, they're not fully a metal. They're kind of a hybrid in between as far as their characteristics go. Now, the further to the left that you go on the periodic table, the more it acts like a metal. The further you go to the right on the periodic table, the more it acts like a non-metal. Non-metals usually, and for the purposes of this class, are often going to form negative ions, and metals are always going to form positive ions, again, for the purposes of this class. Now, why is that true? I made the analogy yesterday that I told you that this last column, these noble gases, their nobility, like kings and queens, everybody wants to look like a noble gas. And if you've ever noticed sometimes what some people will do to try to fit in or to try to look good, they try to look like the celebrities. They try to look like their neighbors. They try to dress like somebody else. They try to have a house that makes them fit in with the crowd. And so what that does may change what they look like on the outside, but it doesn't change what they look like on the inside. And the same thing is true of our friends, the elements, if I can personify them a bit. Everybody on the outside wants to look like a noble gas. And we said yesterday that a noble gas has a full outer shell of electrons. So it has all the valence electrons that it can possibly hold. Okay, and how many is that? Hopefully you said 8. Now I do want to point out that there is one exception to that. Everybody in this last column has 8 valence electrons except for helium. Helium's outer shell of electrons is full when there's only 2. So make sure that you don't get confused with that. This one only has 2 valence electrons because that's all the electrons it has, and its shell is full, but everybody else is going to have 8 in this column. So everybody wants to have a full outer shell of electrons, but that doesn't change what they look like on the inside. And what's on the inside of an atom? the protons and the neutrons, right? The protons are the positive charge and the neutrons don't have a charge. So it doesn't change what's on the inside. It only changes what they look like on the outside. But everybody wants to look like a noble gas. So everybody wants to achieve a full outer shell. So let's see if we can figure out what that looks like. Group 17 has how many valence electrons in it? Hopefully you said 7. So let's say that I have my fluorine atom. He has 7 valence electrons. He wants to look like his buddy neon right next to him. He wants to look like neon. Now he can't be neon because he doesn't have the right number of protons on the inside, but he wants to look like him on the outside. And so if he wants to look like him, he wants to gain another electron so that he can have a full outer shell just like neon does. Well, if he gains another electron, but he doesn't add any more protons, what's that do to his charge? Well, gaining another electron is going to give him a -1 charge. And so everything in this column is going to have a -1 charge to it. The chlorine wants to look like his buddy argon over here. He has 7 valence electrons. If he adds 1 more electron, he'll look just like argon on the outside, and that's what he wants to look like. But gaining another electron will give him a -1 charge. Okay? Now, let's move a column over. Let's say now that I have oxygen. How many valence electrons does oxygen have? Well, it's in column 16, so it has 6 valence electrons. How many more electrons does it need? He's closest to neon. Oxygen wants to look like neon too. And so he wants to gain 2 more electrons. He has 6. He wants to get 8. If he gains 2 more electrons that each have a negative charge on them, he's going to have a -2 charge there. Okay? So sulfur wants to look like argon. Selenium wants to look like krypton. So they want to look like the noble gas that's closest to them by gaining enough electrons to fill up that outer energy level. Okay, so everything in this column will end up with a -1 charge once it's nice and stable. Everything in this column will have a -2 charge. How about nitrogen? Nitrogen has how many valence electrons? Hopefully you said 5 because of the 5 and the 15. It has 5 valence electrons. He wants to look like neon. If he wants to look like neon and have 8, how many electrons does he need to gain? He has to gain 3. Well, if you gain 3 electrons, that now gives you a -3 charge. And so the nitrogen, the phosphorus, the arsenic, they're going to do the same thing. They're going to try to gain 3 electrons so they look like the noble gases in their row. Okay? Now, it's a lot easier to gain just 1 electron than it is to gain 2 or 3. So that means these guys here are very, very, very reactive. They will do almost anything to gain that extra electron. And so that means that they will react very, very easily with another element so that they can gain that extra electron. So these guys are very reactive. Now let's look at what happens over on this side. On this side, they want to look like the closest noble gas. So here, lithium has how many valence electrons? Well, it has 1. If it was going to try to look like neon, which has 8 valence electrons, it would have to gain 7 electrons. That takes a lot of energy and a whole lot of work. And so elements are notoriously kind of like us. They're kind of lazy by nature. And so they're not going to do something if there's an easier way to get to that end result. So lithium isn't going to try to look like neon. Instead, he's going to try to look like helium. Now remember, how many electrons does helium have? Helium only has 2. He has 1 in his valence shell. And so if lithium loses an electron, he will look exactly like helium on the outside. He won't be helium because he still has 3 protons on his inside, but he'll look like helium on the outside, and that's what counts anyway, right? It's how you look on the outside. Just kidding. So the lithium is going to lose an electron. When he loses an electron, what's that do to his charge? it gives him an extra proton, or one more proton than it does electrons. So that means he is going to have a +1 charge. Hopefully that's not too high for you to see that. So anything in this first column is going to do the same thing. Sodium is going to lose an electron so he can look like neon. Potassium is going to lose an electron so he can look like argon. Rubidium is going to lose an electron so he can look like krypton. And when they lose that electron, they will have a +1 charge. What happens to the second column? Beryllium. Beryllium has 2 valence electrons. Anything in this column is going to have 2 valence electrons. So they can either gain 6, well, that'd be a lot of work, or they could lose 2. So beryllium, when he loses 2 electrons, will look like helium on the outside. Magnesium, if he loses 2 electrons, will look like neon on the outside. When they lose 2 electrons, that means they have 2 more protons than they do electrons, and so that will give them a +2 charge when they become an ion. Okay? Aluminum, when aluminum wants to become an ion, he could either gain 5 to look like argon, or he could lose 3 to look like neon, and so that's what he's going to do. So aluminum is going to be a +3 charge. Now notice I kind of made a distinction here because aluminum is a metal and boron is not. So aluminum is going to have this +3 charge because it's going to want to lose those 3 electrons. Okay, so anything in this column, again, for our purposes for this class, we're going to assume that everything in this column is -1, everything here is -2. The non-metals here are going to be -3. Everything in group 1 is going to have a +1 charge. Group 2 is going to have a +2 charge. So I'm going to give you some examples and see if you can come up with this now. So if I give you Na, which is sodium, what charge does sodium want to have? Can you look at the periodic table and figure it out? Sodium is over here. It's in this column, so it wants to lose 1 electron, and so it will have a +1 charge, and so we write it like that. How about bromine? Where's bromine on the periodic table? Bromine is over in this last column. It's right here. And bromine wants to look like krypton, so he wants to gain 1 more electron, and so he will have a -1 charge, just like everything else in that column will. Okay? How about magnesium? Magnesium wants to have what charge? Well, magnesium's over here. What column is it in? He has 2 valence electrons. He wants to look like neon, so he'll lose 2 electrons, and then he'll have a +2 charge. Now, normally when we write that, we write the number first, and then the positive or negative sign. Okay? How about oxygen? Oxygen has what charge? Oxygen's right here. He wants to look like neon. He's going to gain 2 more electrons, so he will have a -2 charge. Okay, aluminum, we said, is right here. It's a metal, so it's going to have a positive charge. It's going to want to gain, or it's going to lose 3 electrons, so it'll have a +3 charge. And then if I look at something like phosphorus, phosphorus is right here. Phosphorus being a nonmetal, well, he wants to gain 3 electrons and look like argon, and so phosphorus would have a -3 charge. Okay, so I want to make sure that you understand how to find these charges. Remember, the whole goal is for them to look like the noble gases on the outside. And so if these guys lose their outermost, if they lose their valence electrons, what's on the outside, then the shell that they uncover is going to look like the one down here. So again, if sodium has 1 electron in its 3rd energy level, if it loses that electron, then everything in the 3rd energy level is gone, and it looks like the 2nd energy level then is full, and it's going to look like neon. Okay? Alrighty, so I'll let you guys get some practice on that.